Hi everyone, so welcome to today's webinar. My name is Tal Semo. I'm Managing Director of Sales and Marketing for Variscite. As discussed today, topic is SecEdge and how we can expand your state-of-the-art security solution with SecEdge and Variscite. Will speak with me later today Mike Hendricks, VP of Engineering of SecEdge, and Ned Ramat, VP IoT Solution of SecEdge, and they will present the more technical part later. Next slide, please. So we'll start off with a quick introduction to Variscite. So Variscite, we celebrated last year 20 years in the SOAR market with very extensive customer base and pipeline. We have our own internal production line for stable supply chain, and we ensure complete control over the manufacturing process. We have very close support from R&D team with 24 hours response on any question or ticket. We are also NXP Platinum membership, which gives us a lot of advantage in both aspects of procurement and early access to NXP solutions. We also provide the most diverse i.MX based product portfolio with the i.MX 6, i.MX 8, and i.MX 9. We meet all the highest quality standards and strict regulatory requirements, including the medical ISO. Both the 9001 ISO, the 13485 medical ISO, and the green 14001 ISO. And we have a quite large ecosystem of partners that can, together with Variscite System, can provide an end-to-end solution. Next slide. So the main advantage of Variscite, so Variscite today keeps two pin-to-pin compatible product families that will enable seamless integration to future technologies, and we'll review that in a minute. We provide the ultimate SOM customization. So Variscite is the only SOM vendor that allows a full customization from MOQ 100 and above, so you can actually select all the features on the SOM and optimize the price. We are committed to 100% yield. So every SOM that leaves our production lines before it ships goes to a full functional test. So we don't have any dead on arrival SOMs. All our products are ready, hardware and software ready. So we have tested the hardware, and of course we have all the relevant kernels and DSP for Linux, Yocto, and other OS as well. It's a very reliable and mature platform. It's been tested and used by hundreds of customers. We provide a lot of free of charge support for our customer to our customer portal system, which you can open tickets and get a very fast response from our support experts, to all our kernels available in the GitHub. We have our developer center, our VariWiki, and of course we provide also CAD drawings, carrier boards, source file, layout source files, and more. Our goal is to support the customer to our development process end to end. We also provide very robust longevity for our product of up to 15 years and sometimes even more. Next slide. So we'll cover shortly now the two pin-to-pin families. Next slide. So this is the first pin-to-pin family. This is the VarSOM pin-to-pin family. It's based on a SODIMM edge connector. You can see that this family goes from the very low-end single-core VarSOM 6UL, which is based on NXP i.MX 6UL single Cortex A7 processor, and then goes to all the older i.MX 6 family with the VarSOM Solo Dual and the VarSOM MX6. And then it covers the majority of the i.MX 8 family of SOM, the MX8, the Quad Max, and the 8M family, the Nano, the Mini, the Plus. Also the MX93, the new i.MX 9 family, and the MX91 is coming soon. And also another SOM which is pin-to-pin compatible, which is based on TI Citara AM62 solution. So all these SOMs are part of the VarSOM pin-to-pin family. Next slide. Then we have the other family. This is the Dart pin-to-pin family. This family is, these SOMs are smaller and using a board-to-board connector. So the primary use is for application with size constraint or need a smaller footprint. So these two pin-to-pin family allow a customer, to migrate from one SOM to the other. Every new SOM you release will be part of these one of these two pin-to-pin families and allow you seamless jump to a new technology in the future with no to minimal change on your hardware side. Next slide. So the advantage of the pin-to-pin family, we talk about scalability, of jumping between different SOMs without changing your hardware. You don't need to redesign while scaling. You can optimize cost and performance, so you can actually design, for example, one carrier board for low-end and high-end products, and of course, ease of development. You don't need to respin your board, and of course, lifetime extensions. So let's say you're using a SOM, get close to its end of life date, so you can jump to a newer SOM with minimal changes. Next slide. So now before we jump into the technical side, we'll just review a quickly. Next slide. So the SOM that was actually SecEdge integrated solution was one of our i.MX 8M Plus based SOMs. So we have two types of them as we discussed. The VarSOM MX 8M Plus, which is part of the VarSOM pin-to-pin family, and the Dart MX 8M Plus, which is part of the Dart. They are both using the same processor, but you see the difference in size. So the Plus is an amazing platform. It comes with the quad-core Cortex A53 1.8 GHz and co-processor M7 with up to 800 MHz real-time processor. It has also an integrated, dedicated machine learning and AI NPU with 3.3 TOPS that can be used and offload the application processor. It supports all the different displays, if it's DSI, LVDS, and HDMI. It has quite attractive and powerful graphic accelerators. It also supports VPU encode decode of 1080p, H264 and 265. It supports dual gigabit PHYs, USB 3, CAN, and CAN-FD. It supports dual MIPI CSI camera inputs, and it supports also as an option built-in certified dual band Wi-Fi 6 and Bluetooth 5.3 with optional of Zigbee 802.15.4. This platform supports up to 8 gigabyte of LPDDR4 memory and up to 128 storage, eMMC storage, gigabyte storage. Of course, we support from commercial temperature 0 to 17 up to full industrial -40 to 85, and longevity is 15 years. So it's an amazing platform, a lot of interfaces, a very attractive price range, and this is why it was selected also by SecEdge as the platform to integrate their solution. Next slide. So just as a summary, you can see here on the VarSOM all the features that are configurable on the SOM. You see you can select your RAM size, the processor type, if it's commercial or industrial temperature, if you need audio codec, if you need Ethernet on the SOM, if you need the Wi-Fi and Bluetooth, and of course storage is also an option, and the storage size as well. Okay, so this covers the i.MX 8M Plus SOM solution from Variscite. Next slide. Okay, now I'll jump to the team in SecEdge and I'll give them the control to go through their implementation. So go ahead.
Thank you, Tal. We want to cover the two parts of our solution. The first part is the edge device security, and we are capable to really provide the foundational security to the edge devices, IoT devices, or edge computing devices. As you may know, security has always been a challenge, and there are two aspects to it. When a device is deployed in the physical world, like the IoT devices are, the attack surface is increased, and there are many physical vulnerabilities. The hacker can just put literally their hands on the device and attack device, probe device, and extract sensitive information relatively easily. So there are also challenges in terms of authenticating the device. And there are many forms of attacks that can be performed directly on these devices. When these devices become connected, the attack surface is even more increased because many more people with bad intention can access the device and do all sorts of things. And privacy, data security becomes a big problem. Remote management of device becomes a big problem. And often these devices need to be accessed by different type of users, the end user for the main function of the device, but also some other companies that maintain the device, for example, or that extract data from the device to provide special services such as analytics or monitoring. So how do we provide security in such an environment? So what SecEdge provides is first chip level security for the device. And one of our major innovations is the ability to do that, leveraging the ARM trust zone. And the advantage of doing it this way is to provide superior security and foundational level security without the need for additional hardware. And we provide a most complete security function to protect the keys, the credentials, the crypto functions, and also now that AI is becoming adopted more and more at the edge level, we can protect the AI and ML model. We can also provide TPM capabilities with software inside the ARM trust zone. And my friend Mike can give you more detail about it in the next few minutes. Our solution has been implemented on various platforms, and NXP is a very big platform, ST, Microchip, NVIDIA as well. And we have already several big customer and partner references to protect particularly the AI at the edge, Lenovo GCI. So two major use cases, the protection of AI and ML model at the edge, and the second is providing the equivalent of a hardware root of trust without requiring a separate chip. And this becomes the foundation to provide what we call chip to cloud security, which I will cover in a few minutes. Mike, do you want to comment this architecture slide?
Sure, Nad, thank you. So as Nad mentioned, when devices are at the edge, they are more vulnerable for the reasons that he laid out just a few minutes ago. And the way that we address mitigation of this exposure is through the use of the ARM trust zone, which is a technology that ARM has provided for a number of years. It's been around for over a decade, so it's not a new technology, but it hasn't been widely adopted outside of a few industries. So one of the things that at SecEdge that we're trying to do is make it more accessible to people who don't have necessarily the large staffs of some, the mobile phone industry and set-top boxes and things like that have a much larger team. And so what we're doing is we're using the trust zone, which provides a secure mode on the chip to have an OS that runs parallel to Linux, so that when you have security functions, you can run those outside of the reach of the Linux system, and that is hardware enforced protection. So the ARM trust zone switches over to the in our case, it's the Core T, the trusted execution environment that runs in the trust zone secure mode, the secure enclave, and then we provide a number of trusted applications that run on top of that to make it easy for somebody to pick up and start adapting these features. And then we also provide a set of APIs to access these trusted functions that you can just link against your application to make sure of these features. One of these applications is the firmware TPM. To access the firmware TPM, it is simply using the TPM driver that is already in Linux. You access it just like you would a discrete TPM. And so you have a number of functions, secure functions now that are outside the reach of Linux to protect your confidential information, such as keys and certificates, and prevent them from being compromised. In addition to the sort of the runtime usage that I was just talking about of how you might use these security features, in order to get the system up and running, there's an additional set of features that have to be accounted for. And so over on the right, in addition to just this runtime, we list here the additional things that are provided in this suite, which include secure boot. So enabling the secure boot features of the chip, making sure that the trust zone, memory, peripherals are configured correctly. One of the, if you go and look at some of the CVEs on the TEE, like OpT, which is an open source project from Linero, what you'll see is a lot of times it's the configuration of the security subsystems and such that lead to those vulnerabilities or those CVEs. And so one of the things, while those systems are open source and references, they do leave the system open a lot of times because they are meant for development, not for locking the system down so that nobody can get into it, because then it becomes a bit of a challenge to do any development at that point. So we provide a number of packages that address the secure boot. Once you lock the system down, then you have and you have diversified keys on every system. How do you address the firmware update? So we provide a path for doing firmware updates of all of those lower level components. We also provide, if your secure boot is now authenticated and encrypted and you're verifying each of the components, how do you do failure recovery if one of those components for some reason fails, your memory becomes corrupted or whatever that reason might be. So we provide, in the secure boot path, we provide an A/B failover, which you can design either to be a fully redundant system, or you can also define it to be a primary system with a small failure recovery system, so that you can reload and move on. We address the provisioning aspect. So when the device is in its pristine state, straight from an XP, you assemble it onto a board. How do you get it initially loaded up with secure software? How do you get payloads, especially if you're using third-party manufacturing, to assemble your devices from these SOMs and such? How do you get those loaded up and protect those payloads that you're putting onto them? So we provide guidance and tools to create encrypted and secured payloads that can be loaded onto the devices, protecting your IP, and then the system itself provides protects IP, and secure storage, and the cloud integration, or what sort of is addressed by the runtime applications there. So I think that is an overview of the basic, a quick overview of the chip level sort of security. Nad, do you want to step forward?
Thank you, Mike. We can come back to this architecture diagram in the Q&A session if there are questions. So the customer benefit when using this security suite called mSpark is that we are capable to provide a very strong hardware-based security, leveraging the Horn trust zone. So this removes the need to add a separate chip, and we enable all the security capability that Mike described quickly here. One particular feature that you may want to pay attention to is the notion of crypto agility, because we are using software methods to do that. This means that your solution, especially in a critical application environment, will be not only very secure, but you could change algorithm over time. There are content security concerns in this space, and this provides a very elegant and powerful solution to address those with this crypto agility capability. And finally, if your customer has a custom security function requirement, those can be also implemented as a TA or a trusted application in the trust zone. So this gives you a very complete security foundation at the hardware level without having any hardware cost. So let me go over now to the connectivity part, and we are providing with what we call the micro-edge solution, edge to cloud security. And the edge to cloud security can start with a chip level security if we implement the ARM trust zone, or if you have in your own development, let's say a discrete TPM. By integrating micro-edge at the device level, we deliver a zero trust networking with an authentication rooted in the hardware of the device. So this provides really an end-to-end security, an end-to-end data security, with also with our architecture encrypted IPsec tunnels. And by doing so, we meet the most demanding security guidelines from NIST, TCG, or in Europe, CRA standing for Cyber Resilience Act. On the cloud side, I will cover the architecture in the next slides. Our solution works in a Kubernetes environment, and it has been designed in such a way that you can deploy easily the solution in a public cloud environment or even an on-premise environment. We do not run the cloud operation. The cloud operation will always be run by your customer or your partner delivering the solution to your customer. And so that the customer cloud requirement, whatever it is, public cloud with AWS, Azure, or Google, for example, our solution can be made to work with those options, as well as on-premise. So our target markets are the secure connectivity for industrial IoT edge application, as well as another segment in the data center space. We provide security for remote server access through the OpenBMC solution. So here is a high-level view of our architecture. You can see three major components. I will start from the bottom part of this slide. Micro-edge is a security agent that works in a Linux environment at the device level. It has a very small footprint. It does not have any negative impact, or it does not add any constraints on the device application. It is essentially an advanced network manager. Micro-edge communicates securely through IPsec tunnel to the backend server equipped with Cloud Edge. Cloud Edge is another software component, part of our solution, and Cloud Edge can be very simply deployed in a virtual machine or in clouds on-premise. So this is something that is very easy to deploy. And all the heavy lifting security functions are handled by Control Edge. Control Edge can be accessed via APIs, so your development complexity is really minimized, and we provide a suite of control function and management function through these APIs via Control Edge. Or if you have a customer requiring the solution to be implemented on-premise, you can also install Control Edge in an on-premise Kubernetes environment. One major important capability of the IPsec tunnels is that not only it provides a very high level of security, always encrypted from the device to the cloud, but devices, application, the security of this communication is automatically enforced. So it is kind of secure by default, if you will. So that's one very important property of this architecture. The second property is that you can have multiple tunnels from one device, and this can have many advantages. It expands the number of services that you can offer to the device, and it can also offer new monetization options. For example, you may be, let's say, a device vendor. You're selling your device, but now you can offer the option to have monitoring or analytics done for these devices by a third party, and those access can be monetized. And those access will be highly secure with the same encrypted tunnels, and Control Edge will be able to monitor all these edges and apply security policies and all the security functions to the endpoints. Now, micro edge can be integrated, as I said earlier, with the hardware root of trust at the device level, and this hardware root of trust can be implemented with the MSpark solution that we discussed earlier. And in that case, there's no additional hardware needed at the device level, or with a traditional TPM, we can also integrate MicroEdge on a device equipped with a TPM. So by doing so, we provide the highest security and privacy with IPsec tunnel. And as you have seen in the previous diagram, the data plane and the separate plane and the control plane are separate. This also increases the security and minimizes the surface of attacks. The deployment complexity is minimized. The only requirement at the device level is Linux, and we have implemented this successfully on various Variscite SOM, starting even with a SOM equipped with a small NXP processor, as well as the i.MX 8, and we were capable to run successfully multiple tunnels on each one of these devices. The Cloud Edge runs on a virtual machine. It is the termination point for the data, and the Control Edge is accessed via APIs. And as I said, this solution is designed to be deployed in a public cloud or on-premise, so that you can meet best your customer requirement without any constraint. You are not locking any particular cloud vendor with our solution. Now, we have another major innovation, which is a cloud SDK that helps you develop and test the end-to-end security solution for IoT and edge devices with great ease and fast. The challenge when we have an IoT project, and we are showing here a typical example. In this case, we are showing two devices connected to a customer cloud, and we are presenting a scenario with a third-party partner providing, let's say, some monitoring function, for example. Now, the development at the device level looks simple, but as soon as you want to deploy this, there are many other considerations that you need to take into account. The secure connectivity, the implementation of the root of trust, testing end-to-end, integrating the solution end-to-end and in a way that scales. And then you want to have your device ready for deployment. Such a project becomes quickly complex because you would need multiple skill, you need expertise beyond the device hardware, firmware, and software. And generally, the impact is that it becomes a big project requiring many months time and many skills to assemble in order to implement it end to end. We have, and this has an impact in terms of cost, in terms of time to market, and in terms of availability of the product ready to be deployed. The solution we have is to use the powerful cloud technology and leverage the virtual environment that is possible with a cloud architecture. So we have developed a solution that is now available through Google Marketplace, and we can implement the solution as in a first step entirely in the virtual world. We are showing here a virtual device connected to the cloud edge and through the cloud edge to the backend application. So it is a very simple and easy way to test your architecture, test the basic communication mechanism and the security policies and control function that you want to have for your deployment as thoroughly as possible. And you can do that at a very low cost with only a few engineers or even one experienced engineer, software engineer would be able to do that. And the IPsec tunnels that are needed here are automatically set up. We leverage the SecEdge, this solution is called SecEdge Studio. The solution on the marketplace has a dashboard, and you can implement and test all this function very easily in hours. We say one engineer, 1 week. It's a little bit of a slogan, but literally one engineer in 1 week can develop and test more than 80% of an IoT security solution in a virtual environment first. So by doing so, we have decoupled the cloud application team dependency on the hardware availability. And after this initial test phase, you can also seamlessly migrate from the sandbox environment to real hardware. And the solution offers a turnkey solution for secure connectivity, and you can move with confidence because the secure connectivity part meets the security industry standards and guidelines. So the first step in SecEdge Studio and Google Marketplace is essentially to architect your system, set up the virtual machine for your device, edge devices, and the backend application. Then you deploy the cloud edge virtual machine. The virtual devices are automatically made ready. The IP connections are set automatically with the cloud tool and our tool, software tool available in Studio. And then after this initial phase of tested, you can even plug in, you can remove the virtual device and connect to Studio, the real device with the real hardware and software. And I mean, it comes equipped with Linux and our MicroEdge agent. You can upload your device application software and continue to the test with the real hardware. As an example here, we are showing what your engineer, your developer will see when he or she accesses SecEdge Studio. This is the opening page of our service on the Google Marketplace. You launch the service and you go through this series of steps. So log in, going to SecEdge Studio product, you subscribe to the product, select your project, and the Google Marketplace, the backend system automatically start the installation process. And you will see in step 7, the OS and the MicroEdge are pre-installed in the virtual machines on the device side as well as on the cloud edge side. The authentication mechanism is done quickly. And the step 1 to 7 or 8 are done within 1 hour. The same thing to be done with real physical devices would take months. Here in 1 hour, you are ready to really do the real part of the project, which is testing end-to-end, testing your security policy, ensuring that the secure connectivity works as intended. So then you can continue the test end-to-end, first in the virtual world in a few days, and then you can move to the physical devices. We are showing here an example of dashboard screen UI. Here we are showing 2 MicroEdge connected 2 devices to 1 cloud edge. And you can see on the right side and the below information related to your connectivity and the overall network status and device messages. Now, after you've done that, here, can you see on the left side, the test in the virtual environment in the Studio, you can continue and move to continue the test with real devices. So basically, you are replacing the virtual device environment with a real device. In this example, it is a Variscite System equipped with both NSPARC, the hardware root of trust implemented in the ARM trust zone, as well as the device application. MicroEdge is, of course, installed also in the device. And the real device will behave in terms of security perspective the same way as the virtual device, so that you can perform the end-to-end test. You can apply policies and things. You can rotate the keys. You can change the certificate management exactly the same way as you have done in the virtual environment. You can do that with an actual device. And the overall effort can be done much, much faster and at a much lower cost than if you were to do everything from the very beginning with actual hardware devices. So that is really the benefit of our solution, of our innovation. So we are turning month-long effort into days. So by doing so, we reduce cost of development for your company, and we help you accelerate the time to market. A single software engineer suffices to do most of this development and test work for the secure connectivity part. It's easy step-by-step process. And you can also test the various security management and policies. For example, we talked about the IPsec tunnels. Those things are deployed automatically. You can also, by the way, even in the virtual environment and with real devices, you can test the notion of multi-tunnels if you want to augment the number of services, or if you want to simulate and test the idea of a monetization with a second tunnel connected to the device to provide to be accessed by a third party. That will be possible as well. So the idea is really to make easy and fast the deployment of actual hardware, and we partner with Variscite, and we have tested this with several Variscite some very successfully. And the idea is really to provide you with a tool that helps you accelerate your time to market and you reduce your cost of development for your project. So that's what I want to cover. Please, we can address questions from the audience.
Yeah, so there are some questions. Let me just pull them up. Just a second.
Okay.
Okay. First question is, how is IPsec better than TLS?
Okay. Okay. So, Mike, you want to start? I will.
Yeah, sure. So this is a question that we get quite often, because a lot of the cloud providers and such just use TLS as the way, or mutual TLS as a way to establish authentication and try to establish secure communication. One of the things, as Ned pointed out, sort of in the architecture, is that MicroEdge essentially establishes the IPsec tunnel, and so everything in the way that we segment that on the devices is with using the Linux namespace feature, and so that the application developers don't have to include the TLS setup in every individual application that may be running on a device, so that it's easier, and your applications can remain a big bit agnostic to the connectivity. They're just using that IPsec tunnel. It appears as an interface, and they just write their application as normal, and then all of the communication going back and forth is through that tunnel. So from ease of development, it just eases that part of it. In addition, because the IPsec tunnel can present a private IP space, then the application and all of that is not actually exposed to the larger to the general internet and the public interfaces that connectivity may be on. So the attack surface for the applications and on all the things that are running through that tunnel are really reduced, because both the application server on the cloud side and the MicroEdge, everything running on the MicroEdge side are now sort of in that private IP space, so they aren't actually exposed to the public space. So I think those are sort of the two of the bigger aspects of the IPsec sort of VPN, like much like, if a lot of corporations in the IT world use VPNs to provide connectivity back to sort of your internal corporate networks. This is like VPN for your IoT devices, and so it makes it easier to manage your applications, because you aren't directly embedding the security of the connectivity into the application directly. You're using the platform and those features, and then also you're limiting the exposure through the IPsec, or through the IP domains or IP ranges that you're using. You limit it to private IP spaces, and I think I think those are probably sort of the biggest two. Nad, did you have anything else you want to add to that, or?
Yes, that's true. These are the most important two, I would say, characteristics of IPsec, the benefit of IPsec versus TLS. I would add to that a couple of more things. One is the notion of multi-tunnel. So this means that one device can be accessed securely by another one or two other third parties very easily, very securely. So these augment the number of services that you can offer as a solution provider, and for the device maker or for the company basically operating the devices, you can have more monetization option. And perhaps even you yourself, if you're a device vendor, in addition to selling your hardware, you can provide security monitoring service for your own devices to your customers. So that could be another source of revenue, as an example. The other part, I think, that is very important, it's a consequence of what Mike described, that compared to TLS, where TLS has to be managed by each application, here it is implemented once, and it becomes, in a sense, secure by default. And this is becoming a requirement by major industry standards, including CRA in Europe. This means that the encryption is enforced automatically. Once MicroEdge is live and running and the IPsec tunnels are established, there is no way for an application to bypass this encryption and leak information outside, which can be done with a poor implementation with TLS. In this case, that risk is completely eliminated. Okay, Tal?
Yes, sorry, I was on mute. So next question is, how much do the FTPM and MSpark impact performance?
Right.
Yeah, I can take that one, Ned. So on the sort of the trust zone architecture, as I mentioned, that is a hardware enforcement of part of the ARM architecture or the ARM cores that are on these chips. And essentially, when you're switching between the trusted and the non-trusted side, it's just a context switch, similar to user mode to supervisor kind of context switch. And so the actual number of cycles that you're performing to do that switch is not very high. I mean, it's hundreds of instructions kind of thing, because you're banking a bunch of registers, sort of getting way down into the weeds here. But so it ends up being a very small impact to do that switch. But then the applications that are running, your security applications, if it's the FTPM, if it's one of the other trusted applications, those are running, are just at that point, they're C applications that are running on the ARM processor. So they're not any less performing than they are in Linux. So if you're running an encryption algorithm, if you run it in Linux or you run it on the T side or the trust zone side, they're using the same core, the same instructions, the same ARM chip. They're running just as fast. So there's not really a performance impact there. The one thing I will say is, if you're running today with no sort of security and you add security, that there is going to be some performance impact, because what if you have to do encryption or decryption, or you're doing signature checks on sort of authentication blocks or something like that, and you aren't doing that today, then there is an impact of you're adding security to your system, and that does use some cycles versus not using those cycles. But that's just the nature of adding security to a system. As far as specifically with the firmware TPM, discrete TPMs tend not to be the highest power processors and compete on those chips. They're really designed. They were really sort of the history on them is they go quite a ways back, and they were mostly used for things like authentication and signature checks and validations and boot sequence checks and those kinds of sort of asymmetric cryptography is what they were kind of designed for, but they weren't the most highest performing platforms. They tended to be, because they're relatively low cost because they're an add-on to the chip. So the firmware TPM, the fact that it is actually running on the ARM core tends to be much higher performing as far as processing speed and everything than discrete TPMs. And that's just due to the nature of the fact that you're running those algorithms on a processor like the i.MX 8 core versus on some type of sort of microcontroller limited scale that would be on a discrete TPM. So from a firmware TPM, you tend to be running pretty significantly better than you would against a discrete TPM. And like I said, those algorithms, the amount of time you'd be waiting for the TPM and things like that, you're going to overall probably see a performance increase on that standpoint as far as your overall application, even though you are using a few cycles to do those algorithms on there. And then the other thing on something like the i.MX 8, you have a lot of cryptographic subsystems, so that gets offloaded to hardware that is designed to do quite a number of algorithms in ciphers, symmetric, asymmetric hashing, the random number generator, all of that hardware is used by the T. And so you get the benefit of those features as well. So overall, using security does have a performance impact. Using the trust zone architecture has a very small, like nanosecond type of impact, because you're just doing a context switch essentially to move between the two. And versus something like a discrete TPM, or even, you tend to have a performance increase. And then as the other thing is, I'll reemphasize a point that Nad made, which is because the firmware TPM is running in the trust zone and is updatable, you have the crypto agility. So the concept that at some point that algorithms become, an exploit or a flaw can be found in an algorithm, and a paper gets published, and all of a sudden, very quickly, what we've thought to be a secure algorithm to exist can sometimes fall very, very quickly because a flaw is discovered. And so the idea of crypto agility, the ability to update your algorithms when those kinds of events happen, is much more straightforward when you have something like the T in the firmware, either firmware TPM or in the crypto TA from the T side, because now you can update your algorithms. Even if you have to move away from the hardware accelerators that are on the chip for some of these things, you can still move over to a software-based implementation of an algorithm to give you flexibility there on those types of things. So I think that's sort of a little bit more explanation on sort of the overall performance of the impact of doing this.
Thank you.
Next question I see is, how many devices can the secure connectivity solution support in one instance?
Good question. How many devices? So one instance of Cloud Edge can support up to 50 to 100,000 devices, so which is a good number. And if you have a project requiring more devices, all you need is just to have the second Cloud Edge installed on a separate VM, and that's it.
Yeah, and I'll add to that from the control edge standpoint, if you're using ours, then you don't have to worry about that. We scale that. If you deploy with the Kubernetes environment for the control edge, that Kubernetes environment is built around a set of microservices and a backend database, so that is scalable depending on the application. It's not like a single VM, so that inherently has flexibility in scaling up to support millions of registered devices, and it's really I think the probably the single thing, as Nat said, is the Cloud Edge instance that you have is the one that you watch the single loading on, and then you can put multiple Cloud Edge instances available for devices, so you can load balance between them and things like that as well. So.
Okay. Thanks, Mike. Last question I see here is if we are going to share this presentation. So the question is yes, we are going to send the presentation to everybody that got registered on this webinar. Okay, I think that the last question concludes our webinar. I'd like to thank everyone for joining us today. You have here on the screen all the ways that you can connect to Variscite. And I wish you a great rest of the day, and hopefully see you again in one of our next webinars. So have a great day, and thank you for joining.